beneath the familiar light of the sun, begins a journey that stretches far beyond anything ever touched by human hands. The sky above Earth appears calm and orderly, scattered with steady points of light that seem fixed and eternal. Yet each of those lights is a star, a distant sun burning through deep time, separated by gulfs so vast that even light itself takes years to cross them. Space is not an empty void, but a quiet ocean, and the sun sits within it as part of a small, loosely connected neighborhood of nearby stars. This journey follows that neighborhood outward step by step, moving away from the warmth of home toward the nearest stellar companions that share this region of the galaxy. The idea of nearby stars can be misleading. In everyday terms, nearby suggests closeness, perhaps something reachable with enough effort. In cosmic terms, nearby still means distances that stretch the limits of imagination. The closest stars to the sun are not just far away, they exist on scales that challenge intuition, where years become units of distance and motion unfolds over centuries. Yet these stars matter deeply. They are the first destinations any future exploration beyond the solar system would face. They are the systems astronomers study most carefully because proximity allows detail. They form the reference points through which the broader galaxy begins to make sense. Every journey needs an origin, and here that origin is the sun. It is easy to forget that the sun is itself a star, one among hundreds of billions in the Milky Way. Its apparent dominance comes not from exceptional power, but from closeness. The sun lies at the center of the solar system, holding planets, moons, asteroids, and distant icy debris in a slow gravitational embrace. Light leaves its surface and reaches Earth in just over 8 minutes, a reminder that even the most familiar warmth arrives with a slight delay. This short span of time represents an intimacy that exists nowhere else beyond Earth. All other stars are separated by years of travel at the speed of light. The sun belongs to a class known as yellow dwarf stars, stable and middle-aged by stellar standards. It has been shining for more than 4 billion years and will continue to do so for billions more. Deep in its core, hydrogen atoms fuse into helium, releasing energy that slowly works its way outward before escaping into space as light and heat. This steady process has shaped every environment within the solar system. It set the conditions for oceans, atmospheres, climates, and the slow unfolding of life on Earth. Without the sun's remarkable consistency, nothing familiar could exist here at all. Despite its importance, the sun is not unusual. Stars like it are common throughout the galaxy, and many of them exist in groups, pairs, or loose associations, rather than in isolation. The sun drifts through the Milky Way accompanied by neighboring stars that share a similar motion through space. These nearby systems are not arranged neatly or evenly. They form a sparse, three-dimensional cloud, with vast darkness between each point of light. Within a radius of roughly 16 light-years, there are dozens of stars and star systems, most of them small, dim, and invisible to the naked eye. Red dwarfs dominate this region, faint stars that burn slowly and quietly for immense spans of time. Leaving the sun means leaving certainty. The distances involved quickly exceed anything encountered within the solar system. Even the outermost regions beyond the planets fade into insignificance compared to the gaps between stars. The heliosphere, the bubble carved by the sun's solar wind, stretches far into space but eventually gives way to the interstellar medium, a thin scattering of gas and dust drifting between stellar systems. Beyond that boundary lies the realm of other suns, each with its own history, structure, and potential worlds. This journey does not rush. It moves outward gradually, from the familiar to the strange, following the order set by distance rather than brightness or fame. The first stars encountered are not the most dramatic or the most visible from Earth. Some cannot be seen at all without instruments. Others shine brightly in the night sky, but hide complex systems behind their light. Each nearby star represents a different outcome of stellar formation and evolution, shaped by mass, age, and environment. As distance increases, time stretches with it. The light arriving from the nearest stars left their surfaces years ago. What is seen now is not the present moment, but a preserved fragment of the past. Every observation becomes a form of archaeology, a study of events that have already happened. This delay grows longer with every step outward, quietly reminding that space is not only vast, but layered with time. The journey ahead traces the shortest paths between suns, beginning with the closest companion to the Sun and expanding outward through the local stellar neighborhood. These are not abstract points on a chart, but physical places, each governed by gravity, nuclear fire, and the slow passage of cosmic time. Together they form the immediate surroundings of the solar system, a small clearing within the immense forest of the Milky Way. Beyond them lie countless others, but understanding begins here, among the nearest lights in the dark. Beyond the orbit of the outer planets, the Sun's influence does not end abruptly. It fades gradually. The solar wind, a constant outflow of charged particles, pushes outward in all directions, carving a vast, invisible bubble around the solar system. This region, known as the heliosphere, acts as a protective cocoon, deflecting much of the high-energy radiation drifting through interstellar space. For decades, every spacecraft launched from Earth remained inside this solar bubble, still moving through territory shaped by the Sun's presence. Only in recent years have human-made objects crossed that distant boundary. The Voyager probes, launched in the late 1970s, traveled outward for more than 4 decades before slipping into interstellar space. Even then, they remained unimaginably close to home on a galactic scale. The heliosphere itself stretches for billions of kilometers, yet it is little more than a thin skin compared to the distances between stars. Once beyond it, the Sun becomes just another point of light behind, indistinguishable from countless others ahead. Here, the darkness deepens. Interstellar space is not completely empty, but it is sparse beyond everyday comprehension. A few atoms drift through each cubic centimeter, remnants of ancient stars and clouds that once collapsed to form new ones. This thin medium carries magnetic fields, cosmic rays, and faint traces of the galaxy's long history. Moving through it means entering a region shaped less by any single star and more by the collective motion of the Milky Way itself. As the distance from the Sun increases, its light weakens rapidly. Within a few light days, it still dominates the sky. Within a light year, it becomes one bright star among many. From several light years away, it would appear as a modest yellow point, easily lost among brighter and larger suns. This is the perspective shared by the nearest neighboring stars, systems that drift through space close enough for their gravitational fields to subtly interact over N. Millions of years. The first of these neighbors lies just beyond the edge of this interstellar crossing. It is not bright. It does not command attention in the night sky. It cannot be seen without optical aid. Yet it is closer than any other star, a faint ember marking the boundary between the solar system and the wider stellar community. This is Proxima Centauri, the nearest known star to the Sun and the first destination beyond home. Proxima Centauri is a red dwarf, a type of star far smaller and cooler than the Sun. Red dwarfs make up the vast majority of stars in the Milky Way, yet none are visible to the naked eye from Earth unless they are extremely close. Proxima is close by cosmic standards. just over 4 light-years away. Yet its light is so faint that it remained undiscovered until the early 20th century. Even now, it requires a telescope to reveal its presence. Despite its small size, Proxima Centauri is a true star, powered by the same nuclear fusion that drives larger suns. Hydrogen fuses into helium in its core, releasing energy that slowly escapes into space. The difference lies in scale. Proxima contains only a fraction of the Sun's mass, and its surface temperature is far lower. The light it emits is reddish and dim, barely illuminating its surroundings. If Proxima replaced the Sun at the center of the solar system, Earth would freeze solid. Yet closeness changes everything. Because Proxima emits so little energy, the region where temperatures might allow liquid water lies extremely near the star. Planets orbiting there must circle tightly, completing an entire year in a matter of days. This proximity brings both opportunity and danger. In recent years, astronomers confirmed the existence of at least one planet orbiting Proxima Centauri, a rocky world with a mass similar to Earth. Its discovery transformed this faint star into one of the most studied objects beyond the solar system. Proxima Centauri is not a calm star. It is prone to sudden flares, violent bursts of radiation caused by tangled magnetic fields snapping and reconnecting above its surface. These eruptions can briefly outshine the star's normal output, flooding nearby space with high-energy particles. For any planet orbiting close enough to receive warmth, such activity presents a challenge. Atmospheres can be stripped away over time, and surfaces exposed to harsh radiation. Whether Proxima's planet can retain an atmosphere remains an open question. Despite these uncertainties, Proxima Centauri holds a special place in human imagination. It represents the nearest step outward, the first star that could one day be visited, at least by machines. Even at extraordinary speeds, such a journey would take tens of thousands of years using current technology. Concepts involving light-driven sails and miniature probes have been proposed, aiming to shorten that time to a human lifetime. For now, these remain visions of the future, reminders of how far the gap between stars truly is. Proxima Centauri does not travel through the galaxy alone. It is bound loosely to a brighter pair of stars nearby, sharing a common motion through space. As distance continues to grow, the faint red glow of Proxima blends into the background, and 2 brighter suns begin to dominate the view. These stars shine with a steadiness more familiar, their light strong enough to be seen from Earth without instruments. They form the Alpha Centauri system, the next landmark in the local stellar neighborhood. Beyond the faint glow of Proxima Centauri, space brightens again as 2 larger stars come into view. Together they form Alpha Centauri, the closest multi-star system to the Sun and one of the most studied stellar neighbors in the sky. From Earth, Alpha Centauri appears as a single bright point of light, especially prominent in southern skies. Only through telescopes does its true nature reveal itself, 2 stars locked in a slow gravitational dance, circling one another over decades. Alpha Centauri A is the larger and brighter of the pair. It closely resembles the Sun in mass, temperature, and overall behavior. Its light is slightly warmer and more intense, but the similarities are striking. This is a yellow dwarf star, stable and long-lived, capable of shining for billions of years. If placed at the center of the solar system, Alpha Centauri A could support a familiar planetary layout, with a habitable region at roughly the same distance Earth occupies today. Its presence offers a glimpse of how ordinary the Sun truly is among the stars. Orbiting alongside it is Alpha Centauri B, a slightly smaller and cooler companion. This star glows with a softer orange hue, emitting less light and heat than its partner. Though dimmer, it is still a substantial star, steady and reliable, with an even longer potential lifespan than Alpha Centauri A. Together, the two stars orbit each share, other in an elongated path that takes nearly 80 years to complete. Their distance varies greatly over time, sometimes drawing relatively close, sometimes stretching far apart, yet always remaining gravitationally bound. For much of human history, Alpha Centauri was believed to be a single star. It was only with improved telescopes that its binary nature became clear. Later still, careful measurements revealed that Proxima Centauri moves through space alongside the brighter pair, bound loosely enough that it drifts far from them, yet remains part of the same system. Together, these three stars form a small stellar family, the nearest such group to the Sun. The proximity of Alpha Centauri has made it a prime target in the search for planets beyond the solar system. For decades, astronomers searched for subtle signs of orbiting worlds, hoping to find planets similar to those around the Sun. Early claims came and went, some later dismissed as artifacts of data or stellar activity. More recently, increasingly sensitive instruments have hinted at the presence of larger planets orbiting at greater distances, though confirmation remains difficult. Smaller rocky worlds, if they exist, remain hidden for now, their signals lost in the complexity of stellar motion. Despite the uncertainty, Alpha Centauri holds enormous importance. Its closeness allows astronomers to test detection techniques and refine models of planetary formation. Any confirmed planet here would instantly become one of the most significant discoveries in modern astronomy, not because of guaranteed habitability, but because of accessibility. Compared to more distant systems, Alpha Centauri represents a nearby laboratory, a place where future telescopes might one day directly image planets, analyze their atmospheres. The system has also captured the imagination of storytellers and scientists alike. It often appears in visions of future exploration, portrayed as the first destination beyond the solar system. From a hypothetical planet orbiting Alpha Centauri A or B, the night sky would look profoundly different. The companion star would shine brilliantly nearby, far brighter than any planet or moon seen from Earth. Proxima Centauri would appear as a faint red point in the distance, a reminder of the larger family to which the system belongs. As the journey continues outward, Alpha Centauri slowly recedes, its twin suns shrinking into the darkness. Their light joins countless others, blending into the background of the Milky Way. Ahead lies another nearby star, far quieter and far less conspicuous, yet remarkable in its own way. It is a star that moves swiftly across the sky, racing through the local neighborhood with unusual speed. This next destination is Barnard's star, one of the fastest moving stars known, and a silent traveler through the dark. Barnard's star emerges from the darkness as a dim, reddish point, barely distinguishable from the background even at close range. It offers no dramatic brilliance, no commanding presence in the sky. From Earth, it is invisible to the naked eye, requiring a telescope to reveal its faint glow. Yet this unassuming star has held a special place in astronomy for more than a century, not because of how it shines, but because of how it moves. Located just under 6 light-years from the Sun, Barnard's star is one of the nearest individual stars beyond the Alpha Centauri system. Its claim to fame lies in its extraordinary proper motion, the apparent speed at which it shifts across the sky relative to more distant stars. First noticed in the early 20th century, this rapid movement signaled that Barnard's star was not only close by, but traveling through the galaxy at a bow. Remarkable pace. Over the course of a human lifetime, its position changes noticeably. a rare trait among stars. Barnard's star is a red dwarf, far smaller and cooler than the Sun. Its mass is only a fraction of the Sun's, and its surface temperature is low enough, but most of its energy is released as infrared light rather than visible glow. This makes it exceptionally faint. If placed where the Sun now sits, its warmth would be insufficient to keep Earth above freezing. Oceans would solidify, and the familiar rhythms of climate would vanish. Despite its dimness, Barnard's star is ancient. Estimates suggest it formed billions of years before the Sun, making it one of the oldest known stars in the local neighborhood. Red dwarfs like this one burn their fuel with extreme efficiency, consuming hydrogen at a slow and steady rate. While massive stars blaze brightly and die young, red dwarfs endure. Barnard's star may continue shining for trillions of years, long after stars like the Sun have faded into remnants. For much of the 20th century, Barnard's star was the focus of intense speculation about planets. Early claims suggested the presence of orbiting worlds, but these signals were later traced to observational errors rather than true planetary companions. For decades, the star appeared to stand alone, a solitary traveler without planets. Advances in technology eventually changed that view. High-precision measurements revealed subtle, repeating motions in the star's light, consistent with the gravitational pull of an orbiting planet. The planet identified around Barnard's star is a super-Earth, more massive than Earth but far smaller than gas giants like Jupiter. It follows a long, cold orbit, receiving only a small fraction of the energy Earth receives from the Sun. This places it well outside any region where surface liquid water would be expected. Temperatures there would be frigid, and any surface would likely be locked in ice. Even so, its existence demonstrates that planet formation occurs even around old, dim stars. Barnard's star itself appears relatively calm compared to some red dwarfs. It does not exhibit the intense flaring seen in stars like Proxima Centauri. This stability has made it a valuable target for studying planetary environments around red dwarfs without the complication of extreme stellar activity. Though its known planet is cold, the system remains a benchmark for understanding how common small planets may be in the galaxy. One of the most intriguing aspects of Barnard's star is its future path. Its rapid motion means it is not simply passing nearby by chance. Over thousands of years, it will continue to approach the Sun, eventually becoming the closest star to Earth for a time before moving on again. Stellar neighborhoods are not fixed. They shift and rearrange as stars orbit the center of the galaxy, drawing closer and drifting apart in slow, inexorable patterns. Leaving Barnard's star behind, the surrounding space grows quiet again. The next nearby star does not rush across the sky or shine brightly. It sits in near invisibility, emitting so little light that it seems almost absent. This star is one of the faintest known in the local neighborhood, a red dwarf whose presence must be inferred rather than seen. Ahead lies Wolf 359, a star that embodies just how subtle and elusive the nearest suns can be. Wolf 359 is located just under 8 light-years from the Sun. Despite this proximity, it cannot be seen without powerful instruments. Its luminosity is so low that even from nearby space its glow barely illuminates its surroundings. Among red dwarfs, it stands at the extreme faint end of the spectrum, a star that burns slowly and quietly, far from the drama associated with larger suns. The mass of Wolf 359 is only a small fraction of the Sun's, placing it barely above the threshold required to sustain nuclear fusion. Its surface temperature is correspondingly low, and its energy output is minuscule. Yet it remains a true star, supported by the same physical laws that govern all stellar objects. Hydrogen continues to fuse in its core, releasing energy at a pace so slow that the star may endure longer than almost any other object in the galaxy. Stars like Wolf 359 reveal an important truth about the Milky Way. Most stars are not bright, not massive, and not easily seen. The galaxy is dominated by faint red dwarfs that quietly persist, while more luminous stars come and go. These stars rarely attract attention, yet they form the backbone of the galaxy's stellar population. Understanding them is essential to understanding the Milky Way itself. So far, no planets have been confirmed around Wolf 359. Its faintness and low mass make detection challenging, and any small planets would produce signals difficult to distinguish from noise. Even if planets exist, their environments would likely be cold and dim, receiving little energy from their star. Still, the absence of known planets does not diminish the star's significance. It serves as a reminder that proximity does not guarantee familiarity, and that some of the closest objects remain the least understood. As Wolf 359 fades behind, its feeble light blending back into the darkness, the journey continues toward stars that grow brighter once more. Ahead lies a system that has been known to humanity since antiquity, a star so luminous that it has shaped myths, calendars, and navigation across cultures. This next destination shines with unmistakable brilliance. It is Sirius, the brightest star in the night sky, and one of the most remarkable stellar systems in the local neighborhood. Sirius announces itself long before arrival. Its light cuts through surrounding space with an intensity unmatched by any other star visible from Earth. From a distance, it appears as a single piercing beacon, steady and brilliant. For thousands of years, this light has drawn attention, guiding navigation, shaping myth, and marking the passage of seasons. Yet beneath that brightness lies a system far more complex than it first appears. Sirius is not one star, but two, bound together in a tight gravitational partnership. The brighter of the pair, Sirius A, is a hot, blue-white star, significantly more massive than the Sun. It burns its fuel at a rapid pace, releasing far more energy and shining far more intensely. Its surface temperature is much higher than that of the Sun, giving it a sharp, almost icy brilliance. This is a young star by stellar standards, still early in its life and radiating with excess energy. Orbiting nearby is Sirius B, a white dwarf and one of the most extreme objects in the local stellar neighborhood. Once a star larger than Sirius A, it exhausted its fuel quickly, swelling into a red giant before shedding its outer layers. What remains is a dense core no larger than Earth, yet containing a mass comparable to the Sun. This remnant no longer produces energy through fusion. Instead, it slowly cools, radiating stored heat into space over billions of years. The density of Sirius B defies ordinary intuition. Matter here is compressed to extraordinary extremes. A small amount of material would outweigh familiar objects by vast margins. Gravity has crushed atoms close together, held in balance only by the strange rules of quantum mechanics. Sirius B represents a future that awaits many stars, including the Sun, a distant endpoint marked by quiet cooling rather than explosive destruction. The two stars orbit each other in a slow, elegant pattern, completing a full cycle over decades. From certain vantage points within the system, Sirius B would appear as a small, brilliant point near its larger companion, its faint light almost lost in the glare. From Earth, however, it remains invisible, without powerful telescopes, its presence inferred through careful observation and calculation long before it was directly seen. Sirius has played a unique role in human culture. Its rising marked the flooding of the Nile in ancient Egypt, becoming a symbol of renewal and abundance. Other cultures wove it into stories of hunters, animals, and gods. Even today, its brightness can cause it to flicker with shifting colors near the horizon, an effect of Earth's atmosphere that has inspired both wonder and superstition. Few stars have been watched so closely for so long. Scientifically, Sirius continues to serve as a benchmark. Its brightness makes it a calibration point for instruments and observations. Its white dwarf companion provides a nearby laboratory for studying stellar evolution and extreme physics. While no confirmed planets are known here, the system remains a focus of interest, not for habitability, but for what it reveals about the life cycles of Cancra. Stars. Leaving Sirius behind brings a noticeable change in tone. The brilliance fades, replaced by subtler lights and quieter sisters. The next stars do not dominate the sky or command ancient reverence. They exist in relative obscurity, faint and steady, yet increasingly important to modern astronomy because of what they may host. Among these is Ross 128, a red dwarf that has drawn attention not for its brightness, but for its calm. Ross 128 lies just over 11 light-years from the Sun. Like many red dwarfs, it is small and dim, releasing only a tiny fraction of the energy produced by the Sun. From Earth, it cannot be seen without optical aid. Yet unlike many stars of its kind, Ross 128 is remarkably quiet. It shows little of the violent flaring common among red dwarfs, making it an intriguing object for study. Orbiting this star is a planet with a mass not far from Earth's. Its orbit places it in a region where temperatures could, under the right conditions, allow liquid water to exist. This does not imply oceans or life, only that the basic energy balance is possible. What makes the system noteworthy is stability. A calm star offers a long window of time during which planetary environments can evolve without constant disruption. Ross 128 serves as an example of how unassuming stars may offer the most interesting possibilities. While brighter stars draw attention, it is these faint, steady suns that dominate the galaxy and may provide the most enduring environments. Advances in observation have transformed such stars from overlooked points into prime targets, reshaping assumptions about where planets, and perhaps complex chemistry, might arise. As distance increases further, individual stars begin to feel less like isolated destinations and more like members of a broader community. Within roughly 16 light-years of the Sun lies a loose collection of systems, dozens of stars scattered through three-dimensional space. Most are red dwarfs. Some exist alone, others in pairs or small groups. A few host known planets, and many more likely do, their signals still hidden below detection thresholds. This local neighborhood is sparse, quiet, and constantly changing. Stars drift slowly relative to one another, their paths shaped by the galaxy's gravity. Over millions of years, neighbors change. New stars approach while others recede. The arrangement seen now is temporary, a snapshot in an ongoing cosmic migration. Among the systems near the outer edge of this neighborhood is Gliese 581. Located more than 20 light-years away, it marks a transition between the nearby and the distant. This red dwarf gained attention for a time because of planets thought to orbit within its habitable zone. Some of those early claims were later questioned, revealing the difficulty of interpreting subtle signals from distant stars. Yet confirmed planets remain, and the system continues to be studied as techniques improve. Gliese 581 illustrates both the promise and caution of exoplanet discovery. Small signals can excite hopes, and later analysis can reshape understanding. Progress comes not through certainty, but through refinement. Each system adds to a growing picture of how common planets are and how diverse their environments can be. As the journey reaches this distance, the sense of proximity begins to dissolve. Stars are no longer immediate neighbors, but distant landmarks. The gaps between them widen, and observation becomes more challenging. Yet even here, within a few dozen light-years, the density of stars is enough to suggest abundance. Planetary systems appear to be the rule rather than the exception. Stepping back from individual stars, the broader view begins to emerge. This small region around the Sun represents only a tiny fraction of the Milky Way. Beyond it stretch spiral arms filled with clouds of gas, clusters of young stars, ancient remnants, and countless unseen worlds. The nearest stars are not remarkable because they are unique, but because they are accessible. They form the first chapter in a much larger story. From the Sun outward to the edge of the local neighborhood, the journey spans more than 20 light-years. In that distance lies a cross-section of stellar life, from young and brilliant to old and faint, from violent to calm. Each system offers insight into how stars form, evolve, and influence the space around them. Together, they anchor understanding, providing context for everything that lies farther away. Beyond this point, exploration becomes increasingly abstract. Stars grow too distant for detailed study, planets harder to detect, signals fainter and slower to arrive. Yet the foundation has been set. The nearest stars define what is normal, what is possible, and what questions remain unanswered. They form the starting line for any future journey beyond the solar system. The local stellar neighborhood may feel small, but it contains enough variety to hint at the galaxy's vast potential. Quiet red dwarfs, blazing binaries, ancient travelers, and fading remnants all coexist within this narrow bubble of space. Together, they remind that even close to home, the universe is rich, complex, and far from fully known. Beyond the systems already passed, the local neighborhood continues to unfold with quiet variety. These stars do not announce themselves with brilliance or myth, yet they fill in the structure of the region around the Sun, revealing patterns that only become clear when broken. Many systems are considered together. Distance alone does not determine importance. Some of the most instructive stars are those that appear almost ordinary, because they reveal how common certain conditions may be across the galaxy. One such star is Epsilon Eridani. At just over 10 light-years from the Sun, it sits comfortably within the nearby neighborhood and shares several traits with the Sun, though it is noticeably younger. Epsilon Eridani is an orange dwarf, slightly smaller and cooler than the Sun, emitting a softer light. Its youth sets it apart. While the Sun has settled into long-term stability, Epsilon Eridani is still restless, surrounded by debris left over from its formation. Observations have revealed a complex system of dust belts encircling Epsilon Eridani, similar in structure to the asteroid belt and Kuiper belt of the ND. Solar system, but far more massive. These belts suggest frequent collisions between leftover planetary building blocks, a sign that the system is still evolving. A large gas giant planet has been confirmed orbiting the star at a considerable distance, its gravitational influence shaping the surrounding debris. This configuration offers a glimpse into what the solar system may have looked like billions of years ago, when planets were still migrating and collisions were more common. Epsilon Eridani demonstrates that planetary systems are not static. They form, rearrange, and settle over immense spans of time. The presence of a giant planet so close to its star by cosmic standards raises questions about how smaller rocky worlds might fare in such an environment. Stability is not guaranteed. And yet, Systems like this help astronomers understand the range of possible outcomes when stars and planets form together. Not far away lies Tau Ceti, a star long familiar to astronomers and science fiction writers alike. Tau Ceti is a yellow dwarf, somewhat similar to the Sun but older and slightly less luminous. Its relative quietness made it an early target in the search for extraterrestrial intelligence, as well as a subject of speculation about Earth-like planets. Over time, increasingly precise measurements revealed that Tau Ceti hosts multiple planets, though most appear to be larger than Earth and located in regions where conditions may be challenging. What makes Tau Ceti notable is not the certainty of habitability, but the caution it inspires. Early optimism gradually gave way to a more nuanced understanding as data improved. This process reflects a broader pattern in astronomy. As instruments become more sensitive, simple stories give way to complexity. Tau Ceti serves as a reminder that proximity does not guarantee familiarity, and that even stars resembling the Sun can host systems very different from its car. Together, stars like Epsilon Eridani and Tau Ceti fill out the middle ground of the local neighborhood. They are neither extreme nor exceptional, yet they offer crucial context. They show how common disks, planets, and long-term dynamical change may be. They also highlight the role of time. A star's age shapes the architecture of its system as much as its mass or composition. Looking across the entire region within roughly 16 light-years of the Sun, a pattern becomes clear. Red dwarfs dominate by sheer number. Larger stars are rare. Binary and triple systems are common. Planetary systems appear to be widespread, though their forms vary enormously. Some stars host tightly packed planets hugging close to dim suns. Others support wide orbits shaped by giant planets and debris belts. Many systems likely host planets that remain undetected, their signals too subtle to isolate with current methods. This neighborhood is not a cluster in the traditional sense. The stars are not bound together as a group. They share space temporarily as they orbit the center of the Milky Way along similar paths. Over tens of thousands of years, the membership of this neighborhood will change. Some stars will drift away. Others will move closer. The map is always in motion, even if it appears frozen on human timescales. Understanding this local region matters because it sets expectations. If planets are common here, they are likely common elsewhere. If stable systems exist around small, quiet stars, then such environments may be widespread across the galaxy. The nearest stars act as test cases. They allow theories to be checked, refined, and sometimes overturned. As attention shifts from individual stars to the collective whole, the scale of the galaxy begins to press in. 16 light-years feels immense when measured from Earth, yet it represents only a tiny fraction of the Milky Way's span. Beyond this neighborhood lie thousands of stars within a few hundred light-years, then millions more filling the spiral arms, and countless others hidden behind dust and distance. Still, every exploration must begin somewhere. The nearest stars are not chosen because they are the most dramatic or the most promising, but because they are reachable in principle. They form the first stepping stones outward, the initial framework upon which all future exploration must build. Any attempt to send probes beyond the solar system, any effort to study exoplanet atmospheres in detail, any hope of understanding how common life-friendly conditions might be, begins here. As the journey continues outward, the stars slowly recede into a broader pattern, less distinct as individuals and more meaningful as a population. Their combined light, though faint, contributes to the galaxy's structure. Their motions trace invisible gravitational currents. Their planets, seen and unseen, add to a growing census of worlds beyond the solar system. For now, The path remains within this quiet bubble of space, where distances are large but still measurable, and where stars can be named, catalogued, and studied in studied detail. Beyond it lies a vastness where such intimacy fades. But before leaving, the local neighborhood offers one final lesson. Even close to home, the universe resists simplicity. It is varied, evolving, and far richer than first appearances suggest. The longer this neighborhood is examined, the more it becomes clear that familiarity does not reduce mystery. Even among the nearest stars, certainty is rare. Measurements improve, instruments sharpen, and data accumulates. Yet many questions remain unanswered. This is not a failure of science, but a reflection of scale. Stars are enormous, distances are vast, and planets are small, subtle companions that reveal themselves only through patience and precision. Within this region, many stars remain poorly known despite their proximity. Some are so faint that only modern surveys revealed their existence. Others are masked by stellar activity that complicates observation. A number of nearby systems contain stars barely massive enough to sustain fusion, objects that hover on the boundary between true stars and brown dwarfs. Though they rarely take center stage, they help define the limits of what a star can be and how diverse stellar outcomes can be. Among the nearby population are several binary systems where two stars orbit closely together. In these environments, gravity weaves complex patterns. Planet formation becomes more difficult, though not impossible. In some cases, planets orbit one star while feeling the distant pull of the other. In others, planets circle both stars in wide paths. These arrangements challenge early assumptions that planetary systems should resemble the solar system. Nature appears far more flexible than once believed. The local neighborhood also contains stars at very different stages of life. Some are young, still surrounded by disks of dust and debris that glow faintly in infrared light. Others are ancient, slowly dimming after burning quietly for billions of years. A few already harbor stellar remnants, white dwarfs that mark the final stage of stars once similar to the Sun. These remnants add another layer to the neighborhood, remind us that stellar evolution continues even here, close to home. Every nearby system contributes a piece to a larger puzzle. How often do stars host planets? How stable are planetary environments over long periods? How do stellar flares, magnetic fields, and radiation shape nearby worlds? The closest stars allow these questions to be explored in detail, setting constraints that apply far beyond this region. What is learned here echoes across the galaxy. As the Sun moves through space, it carries the solar system with it, drifting relative to nearby stars. Over millions of years, the cast of neighbors changes. Stars now considered distant will one day be closer. Others now near will fade away. This motion means the current neighborhood is temporary, a snapshot of a constantly shifting galactic environment. The stars themselves are not fixed landmarks, but fellow travelers following long, curved paths around the Milky Way's center. This perspective changes how proximity is understood. Nearness does not imply permanence. The nearest stars today were not always the nearest, and they will not remain so. Over cosmic time, stellar encounters reshape neighborhoods, subtly influencing comet clouds and distant debris around stars. Even the solar system carries traces of past encounters, recorded in the orbits of distant icy bodies. Despite these changes, the region within a few dozen light-years remains special. It is close enough for repeated observation, close enough for future missions to consider as realistic targets, and close enough to anchor models of stellar and planetary behavior. It is where abstraction gives way to detail where stars are not statistical points but individual systems with distinct histories. Beyond this local bubble, the galaxy expands rapidly in complexity. Star densities increase, backgrounds grow crowded, and distance blurs detail. Yet understanding those distant regions depends on knowledge gained here. The nearest stars calibrate expectations. They reveal what is typical and what is rare. They provide the baseline against which more distant discoveries are measured. As attention drifts outward, the collective presence of these nearby stars begins to feel less like a neighborhood and more like a threshold. Crossing it means leaving behind the comfort of names and measured distances. Beyond it, stars become too numerous to catalogue individually in a single narrative. They merge into populations, arms, and clouds, structures that stretch across thousands of light years. Still, the imprint of the local neighborhood remains. It shows that stars come in many forms even within a small region. It shows that planets are common, but their arrangements are varied. It shows that stability and chaos coexist, shaped by mass, age, and chance. These lessons do not fade with distance. They inform every question asked about the wider galaxy. For now, the journey remains within reach of the familiar, though familiarity itself has been reshaped. The nearest stars are no longer just points of light but complex systems, each contributing to an evolving picture of how stars and planets populate the Milky Way. Beyond them lies a galaxy vast beyond intuition, waiting to be understood through the patterns first revealed close to home. As the view widens further, the local stellar neighborhood begins to feel less like a collection of destinations and more like a quiet framework underlying everyday existence. These nearby stars are always present, whether noticed or not, moving slowly across the sky as Earth turns and orbits. Their motions are subtle, almost imperceptible without careful measurement, yet over centuries they trace gentle arcs that reveal the dynamic nature of the galaxy. Nothing here is fixed. Even the closest lights drift. What stands out most is how empty the space between these stars truly is. Distances of several light years separate systems that appear adjacent on charts and diagrams. If the Sun were reduced to the size of a grain of sand, the nearest stars would be kilometers away. This emptiness defines interstellar space far more than the stars themselves. The galaxy is not a crowded city, but a vast landscape with isolated points of warmth scattered across an immense darkness. Within this sparsity, gravity still plays a quiet role. Though the stars in this region are not bound together as a cluster, their motions are influenced by the same galactic forces. They orbit the center of the Milky Way along similar paths, like leaves carried by a slow current. Occasionally, stars pass closer to one another, close enough to subtly disturb distant clouds of icy debris. These encounters are rare, but over millions of years they leave traces, reshaping the outer reaches of planetary systems. The solar system itself bears evidence of such distant interactions. Far beyond the planets lies a vast reservoir of icy bodies, the Oort cloud, extending nearly halfway to the nearest stars. This fragile structure is easily influenced by passing suns. A close stellar encounter in the distant past may have nudged comets inward, delivering water and organic material to the inner planets. In this way, even stars that never come close still shape planetary histories. Seen from this broader perspective, the nearest stars are not just neighbors but participants in a shared environment. They contribute radiation, gravitational influence, and ancient material recycled through generations of stellar birth and death. Heavy elements forged in long-vanished stars drifted through space before becoming part of new systems. The Sun and its planets carry this inheritance, linking them to stars that no longer exist. This interconnectedness adds depth to the idea of proximity. The nearest stars are close not only in distance, but in origin. Many formed from similar regions of the galaxy, enriched by the same past events. Their compositions reflect a shared history written long before the solar system took shape. Studying them reveals not only individual stories, but a collective past. As instruments improve, attention increasingly turns to the atmospheres of planets orbiting nearby stars. Even faint signals can hint at chemical processes unfolding on distant worlds. Gases such as water vapor, carbon dioxide, or methane become clues, not as evidence of life, but as markers of environment and change. Nearby systems offer the best chance to refine these techniques, allowing subtle features to be teased out of weak starlight. Yet even as possibilities expand, restraint remains essential. The history of studying nearby stars is filled with revisions and corrections. Signals once thought definitive are reinterpreted. Planets appear, disappear, and reappear as data improves. This process is not uncertainty for its own sake, but a gradual sharpening of understanding. The nearest stars teach patience as much as possibility. The idea of travel inevitably arises when contemplating proximity. Though distances remain enormous, nearby stars represent the only realistic targets for future interstellar exploration. Any probe sent beyond the solar system would require centuries or millennia using conventional technology. Even concepts involving light-driven sails and extreme velocities remain theoretical. Still, the nearest stars define the horizon of imagination, setting the scale for what might one day be attempted. In this sense, the local neighborhood is both grounding and humbling. It reveals how much lies just beyond reach, and how small the first steps truly are. Crossing even a single light year requires energies far beyond current capabilities. Yet the fact that stars are separated by finite, measurable distances makes exploration conceivable in principle. The nearest stars transform interstellar travel from pure abstraction into a long-term challenge. As the journey through this region slows, the emphasis shifts from motion to meaning. The stars themselves do not change quickly. What changes is perspective. The sun is no longer central, no longer unique. It becomes one participant among many, distinguished only by familiarity. From afar, its light is unremarkable, one yellow point among others. This realization carries a quiet significance. If the sun appears ordinary from a distance, then its planets are likely not unique either. The processes that formed Earth are not confined to one system. They unfold wherever conditions allow. The nearest stars demonstrate that planetary systems are common outcomes of star formation, even if their details vary widely. At the same time, ordinariness does not imply insignificance. On at least one planet orbiting one average star, matter organized itself into complexity, awareness, and curiosity. That fact alone gives weight to the search outward. The nearest stars do not promise answers, but they provide the first opportunities to ask better questions. From this point, the journey pauses not because there is nowhere else to go, but because the scale begins to shift beyond narrative reach. Beyond a few dozen light-years, stars become too numerous to visit one by one. The galaxy transitions from a neighborhood into a structure, from individual systems into sweeping arms and dense regions where millions of stars crowd together. Yet everything beyond rests on what has been learned here. The nearest stars form the foundation. They show what is typical, what is rare, and what remains uncertain. They anchor imagination to evidence and speculation to measurement. Before leaving this region behind, their lesson is simple and enduring. Even close to home, the universe is vast, dynamic, and still largely unknown. The journey through the nearest stars comes to a natural slowing point here, not because the path ends, but because the landscape changes. Beyond this distance, the character of space shifts. Individual stars no longer stand apart as easily. Their identities blur into populations, their stories woven into broader patterns that stretch across spiral arms and through dense clouds of gas and dust. The intimacy of the local neighborhood gives way to scale. What has emerged from this quiet passage among nearby suns is not a map of destinations, but a framework for understanding. The closest stars reveal how common certain outcomes are. Small stars outnumber large ones. Planets form readily. Stability and violence exist side by side. Time shapes systems as profoundly as mass or composition. These truths do not diminish with distance. They repeat, echoing outward across the galaxy. The Sun now appears in a different light. No longer the unquestioned center, it stands as one example among many. Its steadiness, once taken for granted, becomes a notable trait. Its planets, once thought exceptional, fit within a growing spectrum of worlds shaped by familiar physical laws. The nearest stars make it clear that the solar system is neither an anomaly nor a template. It is one expression among countless variations. This perspective reframes the question of rarity. Life, complexity, and awareness may be uncommon, but the conditions that allow them to arise are not confined to a single star. The building blocks are widespread. Time is abundant. The nearest stars do not confirm anything beyond this, but they demonstrate that the universe is generous with opportunity, even if outcomes remain uncertain. The quiet stars passed along the way also reshape expectations. Brightness does not equal importance. Faint red dwarfs, nearly invisible from Earth, dominate the stellar population and persist far longer than larger suns. Calmness may matter more than brilliance. Longevity may matter more than intensity. These subtle traits influence which environments endure long enough for complexity to take hold. Distance, too, takes on new meaning. 4 light years, 10 light years, 20 light years. Each step outward felt immense, yet all of it fits within a tiny fraction of the Milky Way. The galaxy extends far beyond this region, its full scale almost impossible to grasp. Hundreds of billions of stars lie beyond the local neighborhood, arranged in sweeping arms that curve around a dense central core. Compared to that vast structure, this journey has barely left the threshold. And yet, thresholds matter. Every exploration begins close to home. The nearest stars are the first test of understanding, the first chance to compare theory with reality beyond the solar system. They provide clarity precisely because they are accessible. Their signals arrive stronger. Their motions can be tracked. Their planets, when detected, can be studied with greater detail. They ground curiosity in evidence. There is also a quieter significance woven through this region. These stars have shared space with the Sun for millions of years. Some passed closer in the past. Others will draw nearer in the future. Their motions subtly shape distant comet clouds and the outer boundaries of planetary systems. The solar system has never been isolated. It has always existed within a moving community of stars, influencing and being influenced in return. The nearest stars also remind that permanence is an illusion. Stellar neighborhoods rearrange. Systems evolve. Stars brighten, fade, or collapse into remnants. Planets migrate, collide, or freeze. The universe is not static. It is a slow process of change, unfolding over immense spans of time. The present moment is one frame in a much longer sequence. Standing at this edge of familiarity, it becomes easier to appreciate both scale and limitation. Technology has allowed distances measured in trillions of kilometers to be reduced to numbers and models. Light years have become units of conversation rather than abstractions. Yet the physical reality remains unchanged. Space resists haste. Travel remains constrained. Knowledge advances far more easily than movement. This tension defines the current era of exploration. Observation races ahead. Instruments reach farther. Data accumulates. Understanding deepens. Physical presence lags behind. For now, exploration unfolds through light, mathematics, and patience rather than engines and hulls. The nearest stars are explored not by arrival, but by interpretation. And still, meaning emerges. From these quiet points of light, patterns take shape. The galaxy reveals itself not as a collection of wonders isolated by chance, but as a system governed by shared rules. Stars form, evolve, and fade according to principles that apply everywhere. Planets arise naturally from the same processes. Complexity is not imposed. It grows. The journey to the closest stars does not answer the largest questions. It does something more subtle. It reframes them. It shows that the universe is not built around extremes alone, but around repetition, variation, and time. It shows that even the space nearest to home holds more diversity than expected. It shows that understanding begins locally and expands outward. Beyond this point, the galaxy waits. Its arms stretch tens of thousands of light years. Its core glows behind veils of dust. Its history spans billions of years. The nearest stars are only the beginning, the first chapter in a story far too large to tell all at once. But beginnings matter. From the Sun to its nearest neighbors, a foundation has been laid. A sense of place has formed. The solar system is no longer isolated in imagination. It belongs to a neighborhood, a moving collection of stars bound not by closeness alone, but by shared motion through the Milky Way. In the vast silence between stars, that understanding lingers. The nearest lights fade into the background, their individual identities merging into a broader glow. What remains is context, a sense of scale, a quiet recognition that even here, close to home, the universe is deep, dynamic, and still unfolding.